Hi, General Science. It's a girl, Miss Marshall, coming at you with a brand new video. It is week 5, which is weird because I'm recording it on the Thursday of week 4, but I'm going to pretend that it's week 5 for you guys. Today we are learning about ions and isotopes. So you've learned a lot about neutral atoms. Everything stays the same. Protons stay the same, neutrons stay the same, electrons stay the same. I'm about to blow that up a little bit and say, well, atoms can have different numbers of electrons and neutrons because if we change our protons, we would have a different element. So we're talking about the same element here as we move through. So before we do that, here's your to-do for week 5. Make sure that you're watching this video. So good job. You're already here. Or read the PowerPoint if you don't like listening to me talk. It's fine. I get it. I can be annoying sometimes. Take ion and isotope notes as you are watching this or reading the PowerPoint, and then do the ions and isotope practice, which is in your Google Classroom. Hopefully by the end of this video, you understand why this is so hilarious. This is so funny. I have 2 shirts, not one shirt that has this joke on it, but 2, because it's great. Okay, let's get started. And again, we're running into the issue of me just being here. So what are ions? Ions are atoms that have a net charge due to having a different number of electrons than protons. So we've always talked about neutral atoms. That means that they have the same number of protons and electrons. Well, now they can be different, okay? Atoms will lose or gain their valence electrons in order to, 1, have a full valence outer shell, right? This is our octet rule right here. Or to combine with other atoms to make compounds such as water and table salt. This is called bonding. We're going to talk more about this next week, but just know that this is here. Again, the goal for both this one and this one is to have 8 valence electrons due to our octet rule. I fit here perfectly. Whoa. Yeah. Yep. Okay. So our example that we're going to be working with as we move through this is boron. So a boron atom, when we say atom, we mean neutral. If you look on your periodic table, boron has an atomic number of 5. Right there. I don't know if you could have seen that or not, but it has an atomic number of 5, which means if it's neutral, it has 5 protons and 5 electrons from right here. So when we draw the symbol of a neutral atom, it's just the element symbol. So again, I looked on my periodic table and I found boron and I saw that its element symbol was a B. So that's our atomic symbol right now. No net charge means that there are equal numbers of positive charges, which is protons. That's these blue things right here. And negative charges, which is electrons, which are the red things down here. Oh, hold on. Nope. Okay. So we have equal numbers. I'm going to stop moving my mouse. We have equal numbers of pluses and minuses, protons and electrons. Okay. So a boron ion, notice the change right there. We have a boron atom and the boron ion, which is charged, is in column 13. It has 3 valence electrons. Atoms are only going to lose or gain electrons in their outer shell. So we're focused on their valence electrons here. Hopefully you can read all of that. Boron will lose its 3 electrons to have a full lower shell. So remember in your Bohr model, you had multiple layers of electron shells. Same thing in our actual atom. We have multiple kind of energy levels of clouds. So there's layers. So if I got rid of all of my valence electrons on the outside, that means that the layer right below that would be full, right? So it's good. It's okay to lose electrons. In boron's case, it'll lose all 3 of its valence electrons to have a full lower shell. Why would they lose 3? Well, it's easier to lose 3 electrons than to gain 5 electrons to get 8. So we just think about exchanging things. It would be easier to lose the 3 because it takes a lot of energy to gain 5. That's 5 protons having to attract a grand total of how many? 8 electrons. So that's a lot. Our protons still equal 5. Remember, if we change the protons, then it wouldn't be boron anymore. But our electrons are actually equal to 2. Now, how do I know that? I know that my neutral atom of boron has 5 electrons. If I lose 3, 5 minus 3 is equal to 2. So I have 2 negative charges. Boron now has a net charge of plus 3 because there's 3 more positive charges than negative charges. So let's look down here. My protons are my pluses. My electrons are my minuses, which should show up, right there. So for every plus that we have and for every minus that we have, they cancel each other out. So I have 2 protons and I have 2 electrons. Each of those cancel each other out. So what am I left with? I'm left with my 3 positive charges. So I have a plus 3 charge on my boron ion. Right, so our ion symbol shows, I'm in the way again, shows the overall net charge that's supposed to say in the upper right-hand corner of our element symbol. So we knew our element symbol was a B for boron, and then I'm putting this plus 3, which we figured out in right here. This is our plus 3. So I'm taking that plus 3 and I'm putting it in the upper right-hand corner of the symbol. All elements that have 3 valence electrons, which is column 13, will form a plus 3 charge. Interesting pattern. Now, this is a plus 3. And what's cool about boron is that it's considered a cation. A cation is an ion that has a positive charge. That's it. We just call it a cation. An anion is an ion that has a negative charge. How do we remember that? Well, there's this cool little way that says cats have pos, and so it's a positive charge, right? A cat ion has a positive charge. Here's that cute little kitty, just so you can, help yourself remind that. And then anion, I split it up, an ion, which stands for a negative ion. It's literally in the name. So that's how you can remember it. Or you can say, well, cats have pos. If it's an anion, it's the opposite. It's the other one. Okay. Cool, fun tricks. Lots of those in chemistry. So boron was a cation example. Now let's look at our anion example, which we're going to use fluorine. So a fluorine atom, when we say atom, it means neutral, has 9 protons because the protons make it fluorine, and 9 electrons. When we draw the symbol, we draw an F because that is what it looks like on our periodic table. Okay. You could also see in our periodic table that 9 right there, hopefully. That's our atomic number. So that's telling me how many protons I have. Okay. No net charge means that there are equal numbers of positive charges, which are protons, and negative charges, which are electrons. You can see in the thing below, I want to be able to point to it. What? These guys are your protons and these guys are your electrons. Okay. So every proton has an electron. For every positive charge, we have a negative charge, and they cancel each other out. Let me just freeze for a second and let that bottom thing go away. And now you can see all protons and electrons has a pair. So what happens? A fluorine ion, remember, atoms are neutral, ions are charged, is in column 17 and has, I gotta get out of the way again, has 7 valence electrons. Fluorine would rather gain a valence electron to have a full valence shell than to lose 7. Losing 7 electrons takes more energy, or taking away 7 electrons would take more energy than just gaining one. And actually, fluorine is the best at taking and attracting electrons. We'll talk about that in chemistry, but it's the best element that does that. So it's really going to take that 1 electron. It's very greedy. It wants all of the electrons to itself. So I'm right here. Easier to gain 1 electron than to lose 7, which means that we have 9 protons still, but I gained an electron. So I have my 9 electrons originally, plus 1 electron will give me 10. Okay. We have a net charge of -1 because there is 1 more negative charge than a positive charge. 1 more electron than there is a proton. So we look at our little diagram down here, and we see that for almost every plus charge, there is a negative charge. So we can cancel out every time we have 1 plus and 1 minus, we can cancel that out. So we've canceled out pretty much everything except for that 1 little electron down there. And that 1 little electron will give us a charge of -1. Pretty cool. Move me down again. So our ion symbol shows the overall net charge on the upper right-hand corner of our element symbol. We talked about that with boron, but now we're here in fluorine. And fluorine has that -1 charge, so we put that -1 there. All elements in column 17 have 7 valence electrons, which means they're going to gain 1 electron to have that -1 charge. Whoa, so cool. almost like there's a pattern. What? So let's practice. We'll get to the patterns later. So how many protons, neutrons, and electrons are in the following ions? So in order to determine our protons, we have to look at the type of element that it is, and we have to look at the atomic number. So first one, hydrogen. I grab my periodic table and I say, oh, hydrogen's right here. It has an atomic number of 1. That means I'm going to have 1 proton. Then I need to go and say, oh, its atomic mass, rounded to the nearest whole number, is also 1. My mass number is equal to my protons minus my electrons. Let's put that on here so we can kind of remember, so we can make sure that we're doing this correctly. I can't believe I didn't put it in the thing. Mass number equals protons plus neutrons. You can see that. Okay. So we have protons plus neutrons. So if I have hydrogen, I have a mass number of 1, and I have a proton number of 1. What is my number of neutrons going to be? Well, again, I could say my neutrons are equal to my mass number minus my number of protons. So my neutrons equals 1, which is my number of protons. Hopefully you can see this still. Minus my mass number, which is 1, 0 neutrons. Now, here's the tricky part, and the part that you haven't learned yet. The electrons. Right now, we have 1 proton. We have 1 plus symbol. Yeah, you can see that. Of course you can see that. So we have 1 plus charge. And in a neutral hydrogen atom, we have 1 proton and 1 electron. Okay? But I see that charge. You can't see that I'm pointing to it. I see this charge right here. This says a +1. In order to have a +1, that means I lost an electron. I lost a negative charge. Or I have to have a proton left over. Which means I have to get rid of that electron. So how many electrons do I have right now? 0. 0. Let's see if we got it right. Beautiful. 1 proton, 0 neutrons, 0 electrons. It's pretty cool. Let's try silicone. Silicone Silicone, if I look at my periodic table, has an atomic number. Oh, wrong direction. Has an atomic number of 14. Okay? 14. So that means my proton number is going to be 14. So I'm just going to fill in these blanks here. 14, because that's where my protons go. And then right there. My mass number, rounded to the nearest whole number, is 28. Okay? So I have 28 as my mass number. Now I'm trying to find my neutrons. We already know what our protons are. We know that that's 14. I need to find my neutrons. Okay? So 28 minus 14 does not equal 0. It actually equals 14, which is nice for us because we have the same number of protons and neutrons. That doesn't happen all the time. Look at hydrogen. That's our example. So it happens sometimes, but it doesn't happen all the time. Okay, now we need to figure out electrons. Do I want to draw out 14 electrons? No. So with our electrons, what we need to do is we need to think about, in a neutral atom, I would normally have 14 electrons. But my charge right here tells me that I have 4 protons left over. If I have 4 protons left over, that means I had to lose 4 electrons. And when I lost 4 electrons, that's 14 minus 4, which should equal 10. So I should have 10 electrons in my silicone ion. I should have 14 neutrons, and I should have 14 protons. Let's double check. Boom. Okay. Same thought process with sulfur. Pause me if you need to. Do them yourself. Or you can just keep going, and I'll tell you all the answers. Sulfur, periodic table again, has an atomic number of 16. That means we have 16 protons. It has a mass number of 32. So in order to find my number of neutrons, I need to do 32 minus 16, which, lucky for us, is 16 again. Checking my math. I twitched. Nope. 32 minus 16 equals, boom, 16. So we have 16 protons and we have 16 neutrons. Great. Awesome. Wonderful. Now I need to pay attention to my electrons. My charge tells me, my charge of -2 tells me that I have 2 more electrons than what I started with. 2 more electrons than what I started with, which means I need to add onto the number of electrons that I already had. In a neutral atom, sulfur has 16 electrons because it has 16 protons. But when I add 2, I should get 18. So what I should see is 16, 16, 18. Boom. Okay. Same process with bromine. I'm going to look at bromine. It has -1 charge. My proton should equal 35. My atomic mass rounded to the nearest whole number is 80, which means my number of neutrons is going to be 80 minus 35, which should equal 45. I hope I typed that right because it feels like I didn't. So that should equal 45. And then electrons are going to equal 35 in a neutral atom, but we gained 1, so we should have 36. Why on earth does that say 18? What on earth? Can I change it in here? No. So right now you need to know that this should be 45 because I did not do my math at all, right? No, I didn't. 80 minus 35 is 45. So this should be 45. And I'm going to change this in the original PowerPoint. Of course, I didn't know that. Okay. That is how you figure out protons, neutrons, and electrons in ions. Cool business. All right, so back to the trend I was telling you about. We're going to shrink me again. How can we predict the charge of an ion? How would I know that hydrogen's always going to form a +1 or sulfur is going to have a -2? There's a trend. Since each column has the same number of valence electrons, elements in the same column will also form the same charge. Helpful, right? We need to be reminded of our octet rule. Atoms will gain or lose electrons to get a full shell, which is 8 valence electrons. Whether they lose or gain electrons has to do with how much energy it would take. Okay, so let's move through the periodic table. You have pictures in your fill-in notes that have the periodic table next to every single column that we talk about. I want you to include the charge. So let's look at that. So group 1 elements have 1 valence electron. We know that we did that with hydrogen. To have a full outer shell, group 1 elements have to lose 1 electron or gain 7. Gain 7 or lose 1. Which seems easier? Losing 1, right? So column 1 elements will always lose 1 electron. When an atom loses an electron, there is now 1 more positive charge than negative charge. That means that column 1 forms a +1 charge. Here's that +1. This is what I want you to write in your periodic table on your notes. Okay, cool. Group 2, what's that trend here? Group 2 elements either have to lose 2 electrons or gain 6 to get a full shell. Which one seems easier? Losing 2, saying, go away, I already have a full shell just waiting for me. I don't need you. So they'll lose 2, which means they form a +2 charge. There's that +2 right above that column. Make sure you write that down. Now we're skipping the transition elements because the transition elements are funky. They're weird. They can have multiple charges that depend on their environment. What does that mean? Well, iron right here could have a +3, a +2, or a +1, depending on its environment. Manganese right here, +7, or +4, or a +5. Sometimes a +1 or +2. Zinc typically only forms a +2, but copper right next to it, +2, +3, +1, depends. So we have a different system for finding these out, which you don't even have to learn this year. If you take chemistry, then you'll learn about it. If you don't take chemistry, then you won't learn about it. And I'm sure you'll be fine no matter what. But we are skipping transition elements and going right to our main group, which is group 13 elements, which has 3 valence electrons. Okay? So if you have 3 valence electrons, you can either lose the 3 or gain 5 to make 8. Which one seems easier? Again, it's lose 3 because gaining 5 would take a lot of work. So column 13 forms a +3 charge. Right there. Right, now, group 14 is weird. Group 14 is really weird. And it's a bit tricky. They have 4 valence electrons, which means the toss-up is, do they lose 4 electrons or do they gain 4? It depends. Depends on the environment and depends on the atom. So our ability to gain and lose electrons in atoms has to do with the nucleus, because the protons are what is attracting the electrons to the nucleus. So it depends on the protons. Maybe it'll be easier to lose 4 because the protons are having a tough time holding on to the 4 that they already have. Or it's going to be easier to gain 4 because there's too many protons and those 4 valence electrons already are feeling that pull. It depends. So we say for the column and for the purpose of the trend that column 14 elements will lose 4 or gain 4. Column 14 forms a +4 or a -4 charge. Okay? We just need to know that it's 4, but it could be plus or minus. Depends. I know it's weird. Sorry. Group 15, we're back to normal. Okay? So to have a full outer shell, group 15 elements have to lose 5 or gain 3. Now it's going to be really hard to lose 5 and the atom's going to be really unstable. So they're actually going to gain 3. Oh, there's another mistake in this periodic table. Wow. Sloppy this week. Sorry. I'll fix it in the actual thing. So it is going to gain 3 electrons, which means column 15 forms a -3 charge. 16, lose 6 or gain 2. Easier to gain 2, and that's what it's going to do. Wow, I forgot that too. Oh my God. And so column 16 is going to form a -2. Column 17 is going to form a -1, which we saw in fluorine, because it is easier to gain 1 than to lose 7. Okay, so what does that trend in the periodic table look like? Here it is, +1 for group 1, +2 for group 2, +3 for group 13, plus or -4, depends on the atom, depends on the environment. And when I say environment, it depends on what it's bonding with, really. We're going to talk about that next week, week 6. Here's our -3, -2, -1. And then you'll notice that we didn't talk about the noble gases. That's because they have 8 valence electrons. They don't want to lose any. They don't want to gain any. They're happy the way that they are. They don't need anybody else to, or any other element to bond to, or they don't need to gain or lose. So they're happy. But here's that trend. Make sure you put that in your notes because this is really important. Again, we're ignoring our transition elements. We're going to practice. Okay, what charge will the following atoms form when they turn into ions? Magnesium. Magnesium is number 12. Has 12 protons. It is in group 2. Group 2 has 2 valence electrons. Oh, I clicked on it. Group 2 has 2 valence electrons. It's going to lose those 2. It's going to have a +2 charge. Nitrogen, on the other hand, right there, is in group 15, which means it has 5 valence electrons. It needs to lose 5 or gain 3. It's going to gain 3 to have a -3 charge. Remember, we're writing our charges in the upper right-hand corner of our symbol. All right, that's ions. Gaining, losing electrons, different numbers, same number of protons, same number of neutrons when we would calculate things. But now we're going to talk about isotopes. Isotopes are atoms of the same element, but they have a different number of neutrons. This changes the mass of the atom. Remember our mass number, which I wrote over here, but I also wrote over here, our mass number is equal to our number of protons plus our number of electrons. So here's an example. We have carbon 14. This number right here is the mass of the carbon, that specific carbon atom. Carbon 14 is a carbon atom with a mass of 14 and is an isotope of carbon 12. Carbon 14 is not as common as carbon 12 is. So when we think about carbon in our organic material, in our pencil lead, in diamonds, things like that, we think of carbon 12 because it is the most abundant of the carbon isotopes. So carbon 14 is an isotope. Carbon 14 has 2 more neutrons than carbon 12. How do I know it doesn't have 2 more protons? Because if it had 2 more protons, it would be oxygen. It would not be carbon. So remember, we're just changing our neutrons here. If we change our protons, we change the element. So let's talk about the symbol. The symbol is a lot like the ion symbol, but we have some stuff on the side. So X just means like, hey, your element symbol goes here. And then in the upper left-hand corner, we have our mass number. In the lower left-hand corner, we have our number of protons. Okay, so the isotope symbol for carbon-14 is this guy right here. 14 right here tells us that we have a mass of 14. Here, it has 6 protons, 6 electrons, and 8 neutrons, right? Mass number is equal to, oh, my light's turned off. So mass number is equal to our protons plus our neutrons. If I want to figure out how many neutrons we have, we need to do the mass number minus the number of protons. I don't know if you can see that, so let's blow that up a little bit, okay? Mass number minus our number of protons. If you do not have these written down, you need to write them down somewhere, and that will help, okay? So that's how I figured out that carbon-14 has 8 neutrons. The isotope symbol for carbon-12 is 12 up here, 6 down there, and a C in the middle, okay? Still a 6 because it's still carbon. 12 because it's a mass of 12. That gives us 6 protons, 6 electrons, and 6 neutrons. Isotopes are the reason that the atomic mass on the periodic table is shown as a decimal. So we know that we can't have decimals of or fractions of protons and neutrons. Technically we can, they're called quarks, but quarks don't hold any properties of protons and neutrons. So if we want our proton to have a plus charge, then we can't split it up anymore. So when you look on your periodic table and you see like helium has a mass of 4.0026, then that means that there are isotopes of helium out there. Some of them have a mass of 4, some of them might have a mass of 5. It depends, okay? So that's why we have decimal places in the periodic table. Congratulations, you've learned all about ions and isotopes and a little bit about noble gases this week. And last, there's my meme for the week. Of course, it has to do with chemistry. So remember, I'm going to blow myself up a little bit. Remember, if you have questions or comments or concerns about this material and want to know either more about it or you need some help on it, send me an email. We'll chat over email. If you want to be face-to-face, then I can send you a Google Meet and it'll work just fine. So just let me know. Send me emails. Keep doing what you're doing. A lot of you are sending me work more than I actually expected. So I'm proud of you guys for showing me the work and sending me work, even though a lot of you don't have to because your grades are so good. So keep up the good work. I will see you next week.